Addition of representations tells us which symmetries are present in a reducible representation. And reduction formula decomposes a reducible representation into irreducible ones. Now, multiplication helps us to analyze the interactions between functions, especially when three components are involved, which are the initial state, operator, and the final state. If function A transforms as an irreducible set called tau1, and function B transforms as tau2, then if we want to see under which possible ways these two functions can interact, for that we need a multiplication. Here, it is important to mention that in group theory, when we say multiplication of character, by this we mean it is a tensor product, not a normal matrix multiplication. Because in normal matrix multiplication, when we say M2 multiplied with M1, that means M2 acts after M1. And then we get the final transformation. Here, we will have no information about what the interaction between the two different set of functions yields. But in tensor product, we can investigate each possible interaction between the character of the matrix of an operation. So multiplication of representations tells us the possible symmetry channels through which different functions interact. If under operation, let's say C2 rotation, one function, A, from irreducible representation tau1, transforms like the character chi1 of C2, and another function B, from tau2, transforms like chi2 of C2, where chi1 is the irreducible character of function A for C2 and chi2 is the irreducible character of function B for C2. Then, the all possible interaction between A and B can be described by the tensor product of chi1 and chi2. Let's go to the matrix level. But we need to separate two cases carefully. One is one-dimensional irreducible representations and another one is multidimensional irreducible representations. We already know for a symmetry operation, let's say R, each irreducible representation assigns a matrix, say NR. The character is the trace of the matrix. When the irreducible representation is one-dimensional, then for all symmetry operations, the matrix will have only one element, that is a 1-by-1 matrix. Here the trace is the number itself. So, when we multiply character of operations of two functions, we can multiply directly. That is why, in C2V point group, which contains only one-dimensional irreducible representations, we simply multiply rows. It requires no matrix multiplication complexity. But the scenario changes when we move for multidimensional representations such as E and T. Now, suppose we are in a group like C3V or D3H, where there are two-dimensional irreducible representations. Now things change slightly. If, for a symmetry operation R, a set of function A and B transform under irreducible representation tau1 with matrix M1, R and function C and D transform under irreducible representation tau2 with matrix M2, R. Then, the possible symmetry channels through which A and B will interact with C and D can be found out under the tensor product of M1 and M2 instead matrix multiplication.
The trace of the tensor product of the two matrix will always equal when we multiply the character chi1 with chi2.